All right, friends, we are starting to get to the end of our list of functions to differentiate. Let's tackle inverse trigonometric functions. And like we said in the last couple of videos, we have this inverse trick, right? Let's use it. Let's take our functions, write it in terms of its inverse, and then use implicit differentiation to go from there. We have 6 inverse trigonometric functions to find derivatives of. The inverse sine, inverse cosine, inverse tangent, inverse cotangent, inverse secant, and inverse cosecant functions. Really, we probably could get away with just finding the derivatives of 3 of these inverse trigonometric functions, and the other 3 kind of come along with it. But let's go ahead and do all 6. But first, a quick recap of what an inverse trigonometric function really is representing. So if you have some sort of y equals sine inverse of x, remember, we can write this as x equals sine y. And now we can try and interpret what x equals sine y is really meaning. Normally, the input of our trig functions we think of as angles. So maybe I'll just write angle here. We'd write theta there in a lot of cases, but let's notice y here is representing an angle. And if we want to think about what this specific sine inverse function is doing, there's 2 ways of interpreting this. We can think of the unit circle, and we can say on the unit circle, if you have some sort of a point, maybe we'll pick that point to be right here. I'll make my point a little bit bigger. There we go. With some angle y, now this is going to be a little confusing. We're going to say sine tells us the height of that point. Normally we'd say this is the y value, right? But we're calling our angle y. And the output of this is on the unit circle x. And so what we'll say is that means that's our height. So that's what this is representing. Now this is a little confusing because we seem to be doing this weird swapping of x and y's, and they're representing things that they don't normally represent. So let's just go ahead and think about right angle trigonometry. If you've got a right triangle and y is an angle here, then we know that as long as this actually is a right triangle, the ratio of side lengths that we have, opposite over hypotenuse, is x. Or you can say x over 1. And so that means that we have this set up right here. Sine of y is equal to x over 1. And so there we go. X equals sine y. This is what we're really going to use, this right angle trigonometry setup that we have. All right, so here's our general strategy again. We want to find the derivative dy over dx for some inverse function, right? We're going to look at the flipped around version of these. All of these functions are going to be trig functions. So we're going to have some inverse trig function. We're going to look at the flipped around version of the regular trig function. We're going to use implicit differentiation to find y prime. We want to write y prime back in terms of x, so we're going to need to do a little bit of work, just like we did with logarithms and exponentials. And we're going to use some basic right angle trigonometry to do that work for us. Let's go. All right. Here's this first setup that we described earlier. We want to find the derivative of sine inverse. We're going to use this inverse trick. X equals sine of y. Let's go ahead and get some implicit differentiation going on here. If x equals sine of y, then that means the derivative with regard to x is equal to the derivative with regard to x of sine of y. The derivative of x with regard to x is 1. The derivative of sine of y with regard to x is going to be cosine y times y prime. And we can see now that y prime is equal to 1 over cosine y. This should make some sense here, right? We're okay. We're following along. What you'll notice, though, is that if we wanted to, we could go ahead and take this and compose it inside, just like we did for exponentials and logs and all that kind of thing. But let's just notice that if we do that, we end up with this really ugly layering of trig functions. And in trigonometry, you maybe have simplified those kinds of expressions. I normally don't like the word simplify, because who's to say what's simpler? But we would normally rewrite those without trig functions. Let's just take a look at this triangle that I've got over here. If I want to find cosine y, what is that? Well, it's the adjacent side leg, whatever that is, over the hypotenuse. So let's just find the adjacent side leg using the Pythagorean theorem. We know that the sum of the 2 side legs squared has to give us the squared hypotenuse. So this is going to be the square root of 1 minus x squared. If you square this, you get 1 minus x squared plus x squared. That's going to equal 1. So cosine of y is really the adjacent leg divided by the hypotenuse. So let me just write that here. Cosine y equals the square root of 1 minus x squared over 1. So now what we've got is that this is really 1 over the square root of 1 minus x squared over 1, but I'll just write it this way. That is the derivative of the inverse sine function. Now, the inverse sine function's domain is -1 to 1, and that's because the range of sine is -1 to 1. And so this only works for those values in between -1 and 1, which should make sense. Notice anything outside of that, you're going to get some problems with that square root in the denominator. But that's the derivative of inverse sine. Let's try inverse cosine, and you're going to notice, wait a second, isn't this going to go exactly the same way? This side leg is still going to be 1 minus x squared. So is it going to be exactly the same derivative? Not necessarily, but it's going to be real close. So if we have that x equals cosine y, then the derivative of x with regard to x is going to equal the derivative of cosine y with regard to x. We still have a 1. Notice now we have a negative sine y times y prime, and so y prime is equal to -1 over sine y. And now what you'll notice is that sine y is opposite over hypotenuse. And so we end up with -1 over the square root of 1 minus x squared. It's the exact same form, but because the derivative of cosine is negative sine, we end up with this negative coefficient. That's it. That's the only difference. That's going to be a theme for the rest of these inverse trigonometric functions, because we know that those derivatives are linked by cofunction identities and negative. All right, so here we go. I shouldn't say cofunction identities. I should just say cofunctions. There we go. Derivative of inverse cosine is -1 over the square root of 1 minus x squared. Again, between -1 and 1. Cool. Tangent, let's do it. Let's see how this goes. Maybe what I'll say is just try it. Pause the video, see if you can give this thing a shot. We're going to follow the exact same process that we did earlier. Go ahead and differentiate this and solve for y prime. All right, let's do it real fast. 1 on the left, we're going to do chain rule again. So this is going to be secant squared y. I'm going to attack my y prime here, so no surprises. Y prime equals, 1 over secant squared y. We're going to need the hypotenuse on this thing. So this other side leg right here is going to be the sum of the two squares, right? Because using the Pythagorean theorem. So then what we have is secant of y is going to equal the hypotenuse divided by the adjacent leg. So what's going to happen when we square this? We are just going to end up with 1 over 1 plus x squared. Cool. That is our derivative for the inverse tangent function. Notice that the inverse tangent function does take in any x value it would like, because that's the range of the regular tangent function, -infinity to infinity. All right, now that we have that, how is cotangent going to go? Well, we can already see what's going to happen, right? We switch those side legs, so nothing really happens for the hypotenuse, right? So that's going to be fine. If we have x equals cotangent y, then when we differentiate this, we're going to get pretty much the exact same setup as the tangent one, except the derivative of cotangent is negative cosecant squared y, and then we have a y prime. So y prime, again, is -1 over cosecant squared y. Cosecant of y, we can see, is going to be the hypotenuse over the opposite side, because again, cosecant is the reciprocal of the sine function, so it's going to be the square root of 1 plus x squared. When you square that, you get -1 over 1 plus x squared. Look at that. It's just a negative version of the derivative of tangent inverse. Interesting. All right, Cool. Inverse secant. This one is probably the trickiest one to do. So we'll do this one. We'll go through it carefully, and then we'll kind of just wave our hands and blaze through inverse cosecant because we already are going to see the pattern on how this goes. This one's going to be a little bit trickier, though. So let's write this thing out. If x is equal to secant y, then that means the derivative, again, is equal to the derivative of secant y. No difference here. The derivative of secant is going to be secant tangent, and then chain rule, so tack on a y prime. So again, no surprise. Oops, not tangent x, tangent y. Now you'll notice we've got a couple of things that we have to fill in. One of the things to notice, though, is that we know what secant y is. It's just x. So this thing here, that's x. Then we need to find what tangent of y is. So, okay, now we'll go back to our triangle and we'll use the Pythagorean theorem, and we've got square root of x squared minus 1. So we can see tangent of y is going to be the square root of x squared minus 1 over 1. So that's going to be this thing. But we're going to have to be a little bit careful because x can technically be positive or negative, and that means that this, maybe I'll say it this way, this tangent side length can be positive or negative, right? So really it's like a plus or a minus square root here, and x can be, the output of secant, we'll say, can be positive or negative. I don't want to say x because that's the radius here. But the output of secant, which is x, can be positive or negative. And that's because this side length can be plus or minus 1 if we're in the 4 quadrants. So I don't want to get too hung up on this, but this is really what we have if we just move into like a general like unit circle type trigonometry setup. It really doesn't make a difference to us in any of the other examples, but in this one it can because we have something that was just out here by itself, right? The sign, though, and I don't want to talk too long about this, you can kind of investigate this on your own. The sign, positive or negative, of x versus square root of x squared minus 1 is actually going to end up being the same as each other. Basically, what we're saying here is that when the output of tangent y and the output of secant y are positive or negative, they're positive or negative together here. And so what that means is that this product needs to always be positive. And so the way that we normally write this is actually 1 over the absolute value of x times the square root of x squared minus 1. Again, it has to do with this product here, secant y and tangent y. They end up being the same sign, positive or negative, as each other. And so that ends up being a pretty helpful thing for us to just notice. All right, cool. So, oops, I have another blank slide of that. I don't need that. So this is what we normally have as our derivative of inverse secant here. For inverse cosecant, it's going to go exactly the same way. So we've got square root of x squared minus 1. We can just write this out. The derivative of x is going to equal the derivative of cosecant y. That's going to be a 1. We've got a y prime. We've got a negative cosecant y, cotangent y. So y prime is negative 1 over cosecant y, cotangent y. And again, we have this same idea. And so blah, blah, blah. All this is going to lead to y prime being negative 1 over the absolute value of x square root x squared minus 1. Cool. So that's what we've got. There's tons of discussion on where this absolute value comes from elsewhere. So if you want to really focus on that part, feel free. You can look that up. It'll be in the text assigned to the course, or if you're just watching these on YouTube, you can float around on like Wikipedia or something. It'll have a pretty good explanation of what's going on. But essentially the main idea here is that we need that product to either be always positive or always negative, depending on whether we're working on the secant inverse or the cosecant inverse. So there we go, derivative of inverse cosecant. Quick summary. We don't need to be responsible for the creation of these inverse trigonometric derivatives. It's a nice thing to know. We have that trick. We can use it. It's a helpful trick that we have with that implicit differentiation. But what we really need to be responsible for are these derivatives. The derivative of the inverse sine and inverse cosine functions that are pretty much the same. They're only offset by a negative. The derivative of the inverse tangent and inverse cotangent functions. Again, only difference by a negative. And the derivative of inverse secant and inverse cosecant functions. These three forms, with their positive and negative versions, will pretty much be everything we need to know here. Now, obviously, we can still apply things like product, quotient, and chain rule in examples. Maybe we have a derivative of x squared sine inverse x. No big deal. We'll use the product rule, and along the way, we'll need to know the derivative of sine inverse of x, and so here it is. So these 6 inverse trigonometric derivatives are going to be really important. What you'll notice is that most of the time, people will focus just on these ones. And so really knowing this inverse sine, inverse tangent, inverse secant derivative form is really all we need. Again, for the cofunction ones, they're just negatives. There's other ways of showing that these are just negatives of each other. I like working with that triangle and noticing that the derivatives of the regular functions, the non-inverse trigonometric functions, are negatives, and going from there. But that's all we've got for this. In our next video, it's going to be really short. We're just going to look at derivatives of inverse functions in general. We're really close to that. We have this idea of how to find derivatives of inverses using this implicit differentiation trick. So we'll take a look at that in general, and that'll wrap things up for finding derivatives, and then we'll move on to the next kind of big topic in the course.